We'll start with this top one up here. Find each point of discontinuity of this piecewise function. So with piecewise functions, what you really want to be worried about is where it switches from one value of x to another value of x, like these two places. We want to see at x equals 2, is there a point of discontinuity? So think about what happens the limit as x approaches 2 from the left. And I'm looking at that limit because that's going to use this part of the piecewise function, something less than 2, to the left of 2. And so that limit would be evaluated by plugging in like 1.9999 in for x and seeing what happens. So 3 minus basically 2. 3 minus 2 makes 1. Okay. Now what's the limit as x approaches 2 from the right? If these don't exist, then the limit doesn't exist and it can't be continuous. Right? The limit from the left and the right need to be the same for the limit to exist. So x approaches 2 from the right means we're using this part of the piecewise function, something greater than 2. Something to the right of 2. So if we plug in 2 into this part of the piecewise function, but remember, when you evaluate the limit, you're not doing x equals 2, you're doing x equals 2.0001 or x equals 2.0001, right? So if you plug in 2 divided by 2, that makes 1. So the limit exists. For it to be continuous, f of 2 needs to also equal 1. And if it doesn't, then it's not continuous. Look, f of 2 means that we use this one. This is when x exactly equals 2. No more calculus stuff. Just plugging in x equals 2 means we use 2 for a y value. So the limit doesn't exist. It's a point of discontinuity. So it's discontinuous, d for discontinuous at x equals 2. I'm really tired. So this one, question 22, same type of thing. We want to check at -1. This is x does not equal -1. Okay, so you only use this piecewise function. You use this actually all the time because this is when x does not equal -1. If x does equal -1, then you spit out a y value of 2. So let's do the same thing for this next one, just different color. The limit as x approaches -1, right, because that's my flipping point, -1 from the left. We can be assured that that's going to be the same as the limit as x approaches -1 from the right, because look, if you're a little bit less than -1 or a little bit greater than -1, you use the same function. You're plugging in the same values. So we can just say the limit as x approaches -1 of this function, -1 squared is 1, 1 minus 1 makes 0. So this is going to be 0. And for it to be continuous, we should be able to not just take the limit as x approaches -1, but plug in -1 and get out 0. If it's 0, then it's continuous. But if you plug in exactly -1, it tells us to spit out a y value of 2. So it is discontinuous at x equals -1 for this piecewise function. Okay, last one here. So one place you might check is here. You might not be sure. So think about the limit as x approaches 1 from the left. The y values get infinitely close to 0. The limit as x approaches 0 from the right. The y values get infinitely close to 0. And if you plug in exactly 0, you're going to get out 0. So it is continuous here. Okay, it's continuous at x equals 0. This is a good point to check, though. We know that this is discontinuous without calculus, right? That's a jump discontinuity. The limit as x approaches 1 from the left, we're getting y values infinitely close to 2. The limit as x approaches 1 from the right, as we get closer to 1 coming from the right, the y values are getting close to 1. So the limit as x approaches 1 for f of x does not exist. We don't say equals, I guess. Does not exist. So it's discontinuous at x equals 1 because you can't even evaluate the limit there. And here, the limit as x approaches 2 from the left, we're getting y values of 1. As we're approaching 2 from the right, we're getting y values of 1. But if you plug in exactly 2, you get out a y value of 2. So it's discontinuous here and discontinuous here at x equals 1 and x equals 2.